how I shut my camera off. I hit the wrong button. Okay, the force is proportional to the product of the two masses and inversely proportional to the square of the distance between the point masses. F equals G. Well, okay, so you see that? F is the magnitude of the gravitational force between the 2 point masses. G is the gravitational constant. Okay, this is Kepler's first law. That's what it looks like. Okay. And then I got this picture here from the sun. This is Kepler's second law. As a planet moves into its orbit, a line drawn from the sun to the planet sweeps out equal errors in equal time intervals. And then this is one here. Motion of the solar system, barycenter relative to the sun. And then we have, talks about celestial mechanics. A Kepler orbit describes the motion of an orbiting body as an ellipse. Okay, we saw that already. As a theory in classical mechanics, it also does not take into account the effects of general relativity. Kepler orbits can be parameterized into 6 orbitals. Okay, that's not very good. So barycenter came up, so I looked up barycenter to see what it was, and that's the picture I found. And then the two-body problem came up, which I find interesting because it's got the R1 equals A. I have an R in my equation and an A, so I'm always looking for equations that have those letters in them. The barycenter is one of the foci of the elliptical orbit of each body. This is an important concept in the fields of astronomy, astrophysics, and the like. See two-body problem. In a simple two-body case, R1, the distance from the center of the primary to the barycenter, is given by. So that's what it looks like. Where A is the distance between the center of the two bodies, M1 and M2 are the masses of the two bodies. R1 is essentially the semi-major axis of the primary orbit around the barycenter, and R2 equals A minus R1. The semi-major axis of the secondary orbit, where the barycenter is located within the more massive body, that body will appear to wobble rather than falling in discernible orbit. So two bodies with a slight difference in mass orbiting around a common barycenter. The barycenter is the red cross thing. Okay. The sizes in this particular type of orbit are similar to the Pluto-Charon system and also to Earth-Moon system, in which the center of the mass is inside the bigger body instead. In classical mechanics, the two-body problem is to determine the motion of two-point particles that interact only with each other. Common examples include a satellite orbiting a planet orbiting a star, two stars orbiting each other, a binary star, and a classical electron orbiting an atomic nucleus, although to solve this system correctly, a quantum mechanical approach must be used. The two-body problem can be reformulated as two independent one-body problems, a trivial one and one that involves solving the motion of one particle in an external potential. R is the position of the center of mass, the barycenter of the system. The resulting equation is R equals 0. Shows that the velocity v, I grabbed this because it said velocity, equals dr / dt of the center of mass is constant, from which follows that the total momentum m1 v1 plus m2 v2 is also constant, conservation of momentum. Hence, the position rt of the center of the mass can be determined at all times from the initial positions and velocities, where we have again used Newton's third law, F12 equals minus F21, and where r's displacement vector from mass 2 to mass 1 is defined above. The force between the two objects, which originates in the two objects, should only be a function of their separation r and not of their absolute positions x1 and x2. Otherwise, there would not be translational symmetry, and the laws of physics would have to change from place to place. The subtracted equation can therefore be written. So there's your barycenter with your M1, M2, X1, X2, R, and 0. So it says Jacobi coordinates for a two-body problem is R equals that. Okay. And that's what came up there. And then translational symmetry. Continuous Translation summary is the invariance of a system of equations under any translation. Discretion. Translational symmetry is invariance under discrete translation. Okay, so it doesn't really... I always look for pictures to let me know what it means. So that's the end of that one. And the next one will be Jake 8, line 18A, 3JK.